complex 3. Complex 3 can donate, that can be oxidized and reduce complex 4. Complex 4 can be oxidized and it will donate those electrons finally to oxygen down below, where you're going to end up making water at the very end. Okay? That's a very rough overview in 5 seconds. So what happens when you screw this up? Either by cyanide brownies, what have you. You know, and I hope that nobody took me too seriously and sent your grandmother, you know, who maybe you're looking for her to pay your tuition and need her out of the picture really quick. No, I'm just joking. I hope nobody took me seriously with that. I was just joking. But what can you do what do you expect, or what predictions can you make when you inhibit this? Well, really, come to find out, it's all the same, whether you're dealing with NADH or FADH. Too. So let's go through what you would expect. In the case of, we spoke about rotenone, okay? So it is a complex 1 inhibitor, okay? So what's going to happen? What predictions could you make based off of this? If you inhibit complex 1, so let's walk through it. There's a lot of things here, folks. I'm talking like there's at least like 10, 12 things that you could make predictions off of. That's a lot of test questions, quiz questions. So you would predict that you're going to see an increase in NADH levels, correct? You would consequently not be able to donate those electrons to complex 1, so you would see a consequent reduction, right, in NAD levels, correct? Another way of saying that is you would see an increase in the NADH-NAD plus ratio. That's a third way of saying it. Okay? Does that make sense? The easy way of saying it, and don't forget that the donation of these electrons, that energy, that delta G, that Gibbs free energy, that you're transferring those electrons down the chain, that energy is being harnessed and coupled with the movement of protons from the membrane to the intermembrane space. Okay? From the matrix to the intermembrane space. Does it make sense? All right? So that's one thing. So obviously you're going to predict over time you see less protons, correct? You're going to predict over time you're going to make less ATP. You're going to probably predict you'll see an increase in ADP, right? Because it's just going to be sitting in those beta catalytic subunits, but nothing, there's no proton gradient to actually induce their conformational changes. All right? What about CoQ10? You're going to see an increase in what? Quinone, correct? And a decrease in dihydroquinol. That's just a couple of things here, folks. You can make all sorts of assumptions and predictions on the oxidation or reduction state of complex 3 and 4 too, by the way. Let's go even further back. Think about these electron carriers. If you don't have them present, you know from glycolysis and TCA cycle, you need to have electron carriers to drive the oxidation of fuel, right? So if you're breathing fine, but there's no NAD or FAD around, what are you going to do? Everything's going to get stopped. So up to this point, we're just keeping everything here. But I'm saying you can even go back up those pathways to see what the consequences are going to be. And eventually what will happen is that you will stop glycolysis and TCA cycle. But why is my question. This. Remember in glycolysis, after you take your 6-carbon sugar and you divide it by aldolase, aldolase chops it into 2 3-carbon subunits, and eventually you get 2 moles of glyceraldehyde 3-phosphate, right? That next reaction that converts it into 1,3-bisphosphoglycerate requires NAD. If you're depleting your NAD plus pool, correct? You don't have any way to drive the oxidation of those reactions. So glycolysis will stop. Does that make sense?
But this NAD is in the mitochondria. It's not in the cytosol.
Correct. Correct. But it will eventually back up. It will eventually back up. So, these are some of the predictions that you could make. Now, cyanide we talked about was specific to complex 4, okay? So just keep an eye out, so based off of that, that's a really easy, this is a great way that you can kind of test yourself. How do you screw up this pathway, all right? Now another common thing, this is just with NADH. Now, with FADH2, it's different, okay? Same thing, by the way, that we have written over here would apply, except this, and this would just be replaced with FADH, FAD, FADH2, FAD ratios. Exact same thing would happen, okay? So this is complex 2. We're going to call this CoQ10, 3, and 4. One of the biggest problems with complex 2 is that it does not span the length of the membrane. The physical structure of that complex does not allow it to have any proton pumping activity associated with it. So let me repeat. Complex 2 has no intrinsic proton pumping activity. All right? It has no proton pumping activity at all associated with it. And that is the basis, because as a result of it, you can imagine what you're not going to get are the protons from complex 1 being pumped out. And that's the reason why, from a mathematical perspective, you're not generating the same amount of proton motive force with electrons donated through FADH2 that you are with NADH, which helps to explain why you generate 2.5 moles roughly of ATP from NADH and only 1.5 moles of ATP from FADH2. Okay? Does it make sense? Very, very important point to make. All right? So please, 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 yes?
What's the inhibitor for the FADH2?
We didn't talk about an inhibitor of FADH2. Yeah. Good question to expect, though, on a test, maybe. Same thing. Same exact concept applies. Remember, anytime you interrupt or throw an inhibitor into electron transport, you back it up. You constipate it. Just like you can't push out your poop, this thing can't push out its electrons. All right? And push them forward down the pathway. All right? What else did I get questions on that people were asking me about?